Okay, so in our today's lecture, we are going to finish off section number 2, which is we're going to see describe database administration, including integrity and security control. So in this, we will see database integrity, security control, what that is, and what is transaction in database basically. We just update the attendance sheet. Okay, so what is a transaction in a database management system or DBMS or just database? So in the context of database and data storage systems, transaction is any operation that is treated as a single unit of work. Like, for example, many database administrators, they are updating the database every time, or they are adding some records or deleting something. That those any of the operations that they do is they are considered as a transaction. So that transaction which either completes fully or does not complete at all. Like for example, the classic example of a transaction is what occurs when you withdraw money from your bank account. Like you go to an ATM, right? You insert your ATM card and then the money comes out. So sometimes it happens like your card is stuck and the transaction does not happen and you have to go to the bank. Okay, so either the money has left your bank account, like you have withdrawn the money, or it has not. There can be only two possible options. There cannot be an in-between state, right? So this is an example of a transaction, and transactions are basically fundamental operations in DBMS that allows to modify and retrieve data. Next are basically some asset properties in DBMS. These is basically related with the transaction. So what are asset properties? Asset basically stands for A for atomicity, C for consistency, I for isolation, and D for durability. So atomicity means that the entire transaction takes place at once or doesn't happen at all. There is no in-between state. Like you can take the example of this money withdrawing from your bank account. And then C for consistency, that means the database must be consistent before and after the transaction. So you have done some changes to your database, right? But are those changes consistent or not? Therefore, your database must be consistent even before the transaction also. Next is isolation. That means multiple transactions occur independently without interference. So that means that whatever transaction that you are doing in your database, they are not dependent on each other. Otherwise, there would be a lot of problems, right? And that is without any kind of interference. So all of the transactions are occurring independently. Next, we have durability. So durability means that the changes of a successful transaction occurs even if the system failure occurs. So you can think of this example as you were editing something, right? And that editing, whatever you are doing, is being saved in real time. So at the moment your there was a system failure and whatever editing you were doing, it got stuck because of the system failure. So durability is related with that, like the transaction even occurs even if there is a system failure. Okay, so ACID is basically to ensure the integrity of our database. It is important that these transactions are executed in a way that maintains consistency, correctness, and reliability, even if there is a failure in the database. So this is where basically the ACID properties come into play, and ACID stands for this atomicity, consistency, isolation, durability. These are basically four properties of ACID. So first one is atomicity, or atomicity means basically a transaction is all or nothing. Either like all its operations are succeeding or none are applied. So if any part fails in the transaction, the entire transaction is rolled back, right, to keep the database consistent. And in it, there are also two operations in Tom City. First one is commit. Commit means if the transaction is successful, the changes are permanently applied. Like you were able to successfully withdraw money from your ATM, your bank account. So that change is permanently done. Okay. Next is abort or rollback. So that means if the transaction fails, like you are not able to withdraw money, any changes made during that transaction are discarded. Okay, that is in atomicity. So this is an example here. And in this example, consider the following transaction T. This is a transaction T consisting of T1 and T2. Transfer of $100 from account X to account Y. So before, the X account was containing $500, and after, if the $100 is like sent from or transacted from account X into account Y, then after the X account will be 400 because you subtract 100 from 500, so it's 400, right? And in the Y, what is happening in the Y account? So in account Y, it was before $200. And when the X account sent $100, then after the Y account will be $300. So meaning that this transaction is taking place in just one piece, and the transaction is not failing. Okay, and you can see here the operations here read X. Okay, what is X? Before X was 500, right? And then after it's X minus 100. So you are sending basically $100 to the Y account. And for the T2 transaction, what's happening in the Y account, basically Y plus 100, because it's receiving 100. So that's why 200 plus $100, that's $300. So if the transaction fails after completion of T1, the transaction one, but before completion of T2, the database would be left in an inconsistent state, right? With atomicity, if any part of the transaction fails, the entire process is rolled back or aborted to its original state and no partial changes are made. So either you do the full transaction or you do nothing at all in atomicity. Then we have consistency. Consistency means that the database must remain in a valid state, consistent state before and after a transaction. So you did this transaction T1 and T2. Now look at your database, is it consistent or not? So what does this mean? A valid state or a consistent state follows all defined rules, constraints, and relationships like primary keys, but like all of the things which we have discussed previously, the relationships, the constraints and rules and everything, like primary keys, foreign keys. So if a transaction violates any of these rules, if it violates any of like the primary keys or constraint or relationships, it is rolled back to prevent corrupt or invalid data. And if a transaction deducts money from one account, okay, like it deducted money from the X account, but doesn't add it to another in a transfer, it violates consistency. So next is this example here. So suppose the sum of all balances in a bank system should always be constant, right? But before a transfer, the total balance is $700. Okay, before a transfer, the total balance is $700. After the transaction, the total balance should remain $700. So if the transaction basically fails in the middle, like updating one account but not the other, the system should maintain its consistency by rolling back or aborting the transaction. Okay, so total before this T transaction occurs, that's 700. Okay, and total after the transaction occurs, that should also be 700. After the transaction, basically the total balance should remain the same as it was before. The next we have isolation. Isolation basically means it ensures that transactions run independently without affecting each other. Like all of the transactions which you are doing or which are happening in the database, they are not dependent on each other. They run independently. So changes made by one transaction are not visible to others or do not affect others until they are committed. It ensures that the result of concurrent transactions is the same as if they were run one after another, and this basically prevents issues like reading uncommitted data between changes between two reads, new rows appear during a transaction. Okay, so for example, consider these two transactions T and T prime. X is 500, Y is also 500. So before this X, it's X minus 50, like you are subtracting 50, where basically sending 50, okay, from the T to T prime. So that in this, they will write X and then read Y. Okay, what is Y? Y minus 50. Okay, then write Y, and then in T prime, basically, again read X, the origin value of X, then read Y, and then basically both add X and Y to make Z in the transaction. So in this exact explanation, we have the transaction T, basically, T wants to transfer $50 from X to Y. Okay, so this is okay, $50. That means X minus 50. Okay, then T reads Y. Okay, the value of Y is 500. So it deducts $50 from X, that is X minus 50 here. So the new X would be 450, because if you subtract 500 from 50, that's 450. And then add that 50 to Y. Okay, so now the new Y will be 550. Then what about the transaction T prime? So T prime starts and reads both X and Y, the original X and Y, which was 500. Then it calculates the total sum of both X and Y, which is going to be 1000. Meanwhile, values of X and Y change to 450 and 550 respectively, because you subtracted 50 from X and added 50 to Y. So the correct sum should be 450 plus 550, again 1000. So are you seeing like how if you are adding both of these numbers like 500 and 500, the transaction is the same, 1000. And even if you are subtracting $50 from X and adding 50 to Y, and then you add both of the amounts, it will still remain the same, 1000. So this is isolation. It ensures that T prime does not read outdated values, right? While another transaction, the original one here, is still in progress. So this is what isolation is. Okay, next is durability. Durability ensures that once a transaction is committed or done, its changes are permanently saved, even if the system fails. So the data is basically stored in non-volatile memory because volatile memory like RAM is a volatile memory, and whatever you are doing in RAM, whatever is happening in RAM, when you turn off your computer or laptop, that the whole data is erased off. So that's why it says that the data is stored in non-volatile memory. For example, ROM is a non-volatile memory, right? So the database can recover to its last committed state without losing data. So even if you turn off your PC, turn off your laptop, your data is still saved and you can get back to it without losing it. For example, after successfully transferring money from account A to account B, the changes are stored on the disk, right? And not in the volatile memory. So even if there is a crash immediately after the commit, the transfer details will still be intact, okay, when the system recovers. So this ensures durability. Okay, now how asset properties impact the DBMS design and operation. So the asset properties in totality provide a mechanism to ensure the correctness and consistency of our database in a way such that each transaction is a group of operations, okay, that act as a single unit, but they all work basically independently. They produce consistent results and act in isolation from other operations, and updates that it makes are durably stored. So data integrity and consistency in this asset properties basically safeguard the data integrity of the DBMS by ensuring that transactions either complete successfully or leave no trace if interrupted. So either the transaction is done completely or it's not done. They prevent partial updates from corrupting the data and ensure that the database transitions only between valid states. Then we have concurrency control. So in this, asset properties provide a solid framework for managing concurrent transactions. Like isolation ensures that transactions do not interfere with each other and they all work independently, preventing data anomalies such as lost updates, temporary inconsistency, and uncommitted data. Then recovery and fault tolerance. So durability ensures that even if a system crashes, the database can recover to a consistent state. And thanks to the atomicity and durability properties, if a transaction fails midway, the database remains in a consistent state. What are the critical use cases for ACID or these properties in databases? So in modern applications, ensuring the reliability and consistency of data is crucial, and ACID properties are fundamental in sectors like banking, like how I gave the example of a bank account or withdrawing money from your ATM. So transactions involving money transfers, deposits, even if you transfer money online, okay? So this is an example of asset properties. Or withdrawals must maintain strict consistency and durability to prevent errors and fraud. Then, in the case of e-commerce, ensuring that inventory counts, orders, and customer details are handled correctly and consistently even during high traffic. And this requires asset compliance. And lastly, in healthcare, so patient records, their test results, prescriptions, everything must adhere to strict consistency, integrity, and security standards. Next, we are going to see database schema. What's the database schema? And how do we, like, what are its types and what is it? So a database schema is basically the formal logical and structural blueprint of a database. And in the data schema, like how I have discussed about a relational model, the RDBMS, right, in previous lectures. So as you can see, this is a basically a logical schema. This student ID, student name, and project ID here. That's a logical schema which we make in ADBMS, for example, MS Access or Oracle database or any other DBMS which you are using. But in the physical schema, like in a physical structure, it would be like imagine a big database server which is containing all of the data, right? So that would be a physical schema. Okay, so basically this schema outlines the tables, fields, relationships, views, indexes, everything which we have discussed, like all of the elements which make up a database management system. Okay, so the schema defines a logical view of the entire database, like how your database will look like, and specifies the rules that govern the data, like which table is going to have which relation with the other table, for example, like this. Okay, the types of data which you're going to use, constraints, which constraints are you going to use, relationships, one to one, one to many, or many to one. So think of the schema as an architectural plan for a house, and while the data within it is the furniture. What are the key aspects of a database schema? First one is the structure and organization. So a database schema, it defines table structures, including column names and data types, which we discussed, right? Integer, varchar, date, all of that. Then relationships, it maps out how many, like how different tables or entities relate to each other, relate to one another. Which table is going to have a one-to-one relation, which one is going to have many-to-many, like that. And then constraints, so it sets rules for data integrity such as not null, unique, and check, all of the constraints which we did in the previous lectures. Next is static nature. So unlike a database instance, which is basically a snapshot of data, specific time and changes frequently, schema is generally static and stable. Okay. Then what about representation? So schemas can be represented visually via ERD diagrams. ERD diagrams are diagrams which we use to make logical schemas. Okay, they basically highlight which table has one relationship, and the column names and everything basically, or encode using data definition language DDL like SQL, or maybe you can use Oracle database management system or PostgreSQL or Microsoft SQL Server to make database schemas. In either way, both can be done. So in simple terms, the schema provides the framework that makes it easier to understand, manage, and use data in a database, and it's created by database designers to ensure that the data is consistent and efficiently organized. Next, we are going to see types of database schema. So first one is the conceptual database schema. The conceptual schema or database schema describes the overall structure of the entire database at a high level. It basically focuses on the meaning of data and captures how different entities relate to each other. And its key points are that it represents a whole database for the entire organization. Okay, describes the entities, attributes, and relationships. So the table names, for example, is student. It is 5 column student name, and this student table has one-to-one relation with the course table, for example. Okay, then it's technology independent. It does not depend on SQL or storage or hardware, and this is basically usually designed using ER diagrams. Okay, and it acts as a bridge between user requirements and the logical schema. Okay, might show you what's an ER diagram. So it looks like this basically, and this is what it looks like. These are the rectangle one, the one in the rectangle. These are basically your entities. Okay, and in when you are basically making an ER diagram, you convert this ER diagram into a data definition language, like in your MS Access, for example, or Microsoft SQL, MySQL, or any kind of DBMS which we discussed, which you can use to create your database. So the ones in rectangle, the rectangle ones, these are your entities. Okay, we call them entities. And when you convert this entity into a database, into a like a logical schema, that will be your basically table name. So table name is going to be employee. Okay, and then what about these oval shape? These oval ones are basically your attributes, like the columns, which I also told you that attributes are also known as columns in database. So these oval ones, these are your attributes or columns. So table name is employee, column is name, ID, gender, address, DOB, DOG. Okay. Okay. What about this shape here, the diamond shape? Okay. This diamond shape is basically showing you the relation between the employee table and the department table. So employee works in department. Employee is dependent of this. This is another, basically it's a whole ER diagram kind of thing, but this is what it looks like in actuality. Okay, and this is a conceptual database schema. If someone were making a conceptual database schema, they would use usually an ER diagram like this. Student table. Okay, student study this course. Course table has course ID, course name. So these are basically the student and course are entities, and the ones in the oval shape, these are the attributes or column names. Okay, next example is a conceptual schema for a school system includes entities such as students' courses, like I gave the example here, this one. Okay, so it's a conceptual database schema. Next, we have the physical database schema. So the physical schema defines how the data is actually stored on the disk. So it specifies files, indexes, partitions, storage blocks, access paths, all of that. It represents the lowest level of abstraction, focusing on performance, storage optimization, and data retrieval efficiency. And what are key points? Key points that it determines the physical layout of tables and indexes, depends on the specific DBMS, like which kind of DBMS you're using, MySQL, Oracle, PostgreSQL, MariaDB, whatever it is. And it is mainly designed by the database administrator, DBA. The one who designs this is the database administrator. Next, we have the logical database schema. So the logical schema describes the logical structure of data as it appears to the database designers and developers. Like if someone were looking at the logical database schema, they would understand immediately which one is the, like how many tables there are and which table have a like relation with each other. Okay. So this is what a logical design or logical database schema looks like. Countries, that's your table name. Okay. Then country ID with this data type, like what this data type you will specify, okay, with your column name or your attribute. Okay, so then the residence table, it has this resident ID, which your primary key, resident name, birth year. That's all of these basically the resident ID, all of these are attributes of column names. And the arrows are basically showing the relationship. Okay, so cities is having a relationship with residents, then countries is having a relationship with cities, or cities having a relationship with countries. Like you can see, countries have cities, okay, or cities are made up of countries. Cities have residents, like this. We use this logical database design. Okay, so in this we define tables, columns, primary keys, foreign keys, relationships, and integrity rules. And this ensures that data is structured properly, relationships between tables are meaningful, integrity rules maintain data accuracy during operations. So this schema represents a higher level of abstraction and is independent of physical storage details. And it is built from the conceptual schema using ER modeling. So as I said that you will use the ER model, okay, to build your logical schema or logical design. This is how it looks like. So you convert from ER diagram to logical database design. And this focuses on how data is logically organized, now how it is stored physically. Because then physically it will be stored on the disk but different. Next, we have the view database schema. So the view schema is the highest level of abstraction, showing how individual users or applications see the database. It defines basically customized views tailored to users' needs. So users interact with these views without knowing about the underlying logical or physical infrastructure. Users just have to interact with the database. They do not have to know about like how did the database administrator physically, manage this, or what is the logical structure of this database. Okay. For example, a student sees only their own marks and courses, right? And admin sees all student records. Both are different view schemas and for different users. So student, you will not give the student access to everything, right? You will only give the student access to their own marks and courses. Then again, admin is, because he is the administrator, so he's gonna have all of the access to everything. So a database can have multiple view schemas, each showing only part of the data. And it depends how many users there are and what is their function basically. Then next, this is basically levels of data abstraction, showing first of all the physical level, physical schema, then conceptual database schema or the logical schema. Then there is the view schema. Okay, so this user one is the student, he sees only his marks and GPA. Then second is the teacher, for example, the teacher only sees the students' records and everything. Then we have admin and so on and so forth. Next is we have database schema designs. So schema design mostly depends on the application's requirements. Who are you designing this database for? Okay. First one is we have the flat model. So flat model schema is a 2D array. It's kind of like this, okay? Rows and columns. There's a flat model in which basically every column contains the same type of data or information, and the elements with rows are related to each other. So it's just like a table or a spreadsheet, like how you work in Excel sheets or Google Sheets, just like that. So this schema is better for small applications that do not contain complex data, right? That's a 2D model, a 2D array. Then we have the hierarchical model. So data is arranged using parent-child relationships. Like every parent has, for example, three children. Each child is related to the parent, and it's a tree-like structure in the hierarchical database model because each record consists of several children and one parent. That means there's one parent and then several children. So it can be used to illustrate one-to-many relationships in diagrams such as organizational charts. It looks like this. Okay. You have the electronics, okay, and in electronics you have the televisions. You can divide the electronics basically into televisions and portable electronics in some other types. And then in televisions you have different basically types of televisions. So there's tube, LCD, plasma, LED, so on and so forth. Then in portable electronics you have the MP3 players and all of that. So basically where is the parent? The parent is the electronics, and the parent has two children, televisions and portable electronics. Then again, televisions is acting as the parent here, and it has three children, tube, LCD, and plasma. As same for the portable electronics here. So this one is a hierarchical model which shows basically a parent-child relationship or a one-to-many relationships. Then we have the network model. So it's similar to the hierarchical model in that it represents data using nodes or entities and edges or relationships. But unlike the hierarchical model, which enforces a strict parent-child relationship, the network model allows for more flexible many-to-many relationships. Okay, in the hierarchical model, you can only have one-to-many relationships. Okay, one parent, many children. Again, the one television, many children. So again, this MP3 player is one parent and this one children, or it could be any other children also. Network model is not like this. It has flexibility, means that a node can have multiple parent nodes, okay, and child nodes, making the structure more dynamic. So it looks like this. Okay, now you can see there is a parent project here. It has two children, project one and project two. But now this project one has multiple children, like department A, department B. It's also having a relationship with the department C, which is actually a part of project two. So that's a many to many relationship right there. Next, we have the relational model. In the relational model, that's used for relational databases or RDBMS, where the data is stored as relations of the table in like rows and columns. Okay, here you can see it looks like this. You have the columns or the attributes in which you will have identifying all of the basically the data types which you are going to use. So student ID is your primary key, okay? And see, the rows are also called as records or tuples, okay? And the attributes here, they are also called as columns or fields, okay? This is a relational model or RDBMS. Then we have the star schema. So star schema is better for storing and analyzing large amounts of data. When you have, so it has a fact table at its center and multiple dimensions table connected to it, just like a star. Like how there's a, you can think of it as a star. Okay. So 1, 2, 3, 4, and 5. So if you draw a star, it will be like this. Okay. In the center, you have the fact table, and this part of the star, that's your dimension table. This one again, table. Okay. So it will have a star-like structure. Then we have the snowflake schema. So just like star schema, the snowflake schema also has a fact table. It's like a snowflake. Okay. Like how in winters we have snowflakes. So, but the main difference in both models is that in snowflake schema, dimension tables are further normalized, okay, into multiple related tables. And this is also used for analyzing large amounts of data. So this is a snowflake schema. Okay. There's you can call this one here, this part, that's your star schema. Okay, but now that this is not a star schema, because now this dimension table is again divided into, or it has again multiple branches like subdimensional table. So now it's not a star schema anymore, it's a snowflake schema. Okay, next is role of database administrators, skills and responsibilities. So what's a database administrator? Database administrator is basically an IT professional who is responsible for installation, configuration, maintenance, and security and performance of an organization's database, right? Of a database management system. So the DBA handles tasks include database installation, configuration, security management, user authorization, who to give basically access to, performance monitoring, backup and recovery. And DBAs ensure that data is available, secure, reliable, and consistent. They act as custodians of an organization's most valuable information assets. What are the core responsibilities of a DBA? So first one is the database installation and configuration. They need to install and upgrade DBMS software, for example, SQL Server, whatever like the organization is using, okay, and manage the underlying infrastructure. Next is security management. So implement security measures such as access controls, encryption, authentication protocols like RBAC to protect sensitive data, like which people should have access and which should not have access. Then we have backup and recovery. So develop and execute backup strategies to prevent data loss and perform recovery operations in the event of system failures. They should be able to keep backup of all of the data. Then performance monitoring and tuning. So tracking database performance to identify any bottlenecks, any kind of anomalies, problems, and optimize the queries, make them go faster, and adjusting configurations for maximum efficiency. Next, we have the capacity planning. So monitoring storage capacity, right, and data growth to plan for future resource needs. Next is troubleshooting. So that means identifying, investigating, and resolving database errors, connectivity issues, and performance degradations. And lastly, data modeling and design. So assist in designing the physical structure of the database. That's also the responsibility of that database administrator. Create indexes and maintaining data integrity. Okay, what are the skills required for DBA? Like what should a database administrator skills have? First of all, good communication skills and excellent knowledge of databases, architecture and design, RDBMS, because without these, no one can be a database administrator. Then knowledge of SQL, structured query language, expertise in database installation, configuration and upgrades, and knowledge of backup and recovery techniques, problem solving and troubleshooting skills, right? Knowledge of cloud database platforms and virtualization. Because if the company decides to move to cloud, then the database administrator should be able to move the database and the physical servers and everything to the cloud also. And lastly, experience in backup, restore, that disaster recovery planning, understanding of compliance, like the laws and database security standards. So all of these skills are necessary for a database administrator. Next is the types of DBA. So first one, we have the general purpose DBA. That means this DBA handles all aspects of database administration. Then is system DBA. So this system DBA focuses on only the technical aspects, including the installation, configuration, and operating system interaction. Then we have the application DBA. So the application DBA specializes in supporting specific applications, okay, writing complex queries and managing test data. And then we have the task-oriented DBA. So task-oriented DBA focuses on specific critical tasks like backup and recovery or performance tuning. And then we have the cloud DBA. So manages databases hosted in cloud environments, for example, AWS, Azure, GCP, or other cloud environments, focusing on provisioning, scaling, and cost management. Then lastly, we have data warehouse DBA. So this DBA designs and maintains data warehouses handling ETL, that stands for extraction, transformation, loading processes. Okay. Next is database security, integrity, and control. Like why is database security important? What is included in that? Okay. So database security uses authentication that can include passwords, MFA, authorization, and encryption. Integrity basically ensures that database is consistent, okay? And it enforces data quality via constraints, and control mechanisms include auditing, backups, and views. So in database security, confidentiality and availability, security ensures that only authorized users can access the database, protecting from malicious or accidental damage. So first one is authentication. That means verifying user identity via passwords or multi-factor authentication. Then authorization and access control. So granting specific permissions to specific users, read, insert, update, delete. Okay, who should read, who should be able to insert, and who should have every permission. Then role-based access control, also called as RBACs. That means assigning permissions to roles rather than individuals, simplifying management. Next, we have encryption. That means protecting data at rest and in transit. Encrypt the data. Okay. And next is vulnerability management. So applying security patches, regularly updating your database, okay, scanning for any potential risks. Next, we have inference control. It means preventing users from inferring sensitive information from statistical data. Next, we have database integrity, accuracy and consistency. That means integrity ensures the accuracy, correctness, and validity of data stored. So first one is that it ensures each table has a primary key that is unique and not null. And then enforce the differential integrity. So maintains consistency between tables using foreign keys to prevent invalid data links. We have discussed all of the integrity and constraint types in the previous lectures. So this is all about that. Next, we have the domain integrity. So it restricts basically values for an attribute to a defined set or a defined domain. For example, data type, range, constraints like that. And next we have user-defined integrity. So in the user-defined integrity, that enforces specific business rules such as check constraints. And lastly, in database control mechanisms basically manage how the database operates, right, and how data is changed. So first one is auditing in the database control. That means it will track user operations, who accessed the data at what time, when, and what like that person do with the data basically. And next we have backup and recovery. So regularly save data to prevent loss in case of any disaster. Next is concurrency control. So managing simultaneous access to ensure that data remains consistent during updates. And lastly, views. So that means limiting user access to specific rows or columns of a table. So that was about section number 2, which is fully completed today. And we discussed the database administration, including integrity and security control, transaction properties, and everything. Okay, see you in the next lecture. Inshallah. Allah Hafiz.